begin, but I hope that offers some perspective from a systems data science perspective on the contemporary scene. One of my biggest fears, I teach these courses on, AI for public health. One of my biggest fears is that we're going to be turning people into just folks who say, well, okay, we have a lot of data, let's put it into the algorithm and see what it says. No, come on, it's just yearning to tell you these things if you have an understanding of the data generating process. Think, folks, think mechanistically about why we see these things. And if you're a software engineer, and I'll be with you in a second. If you're a software engineer, okay, now I'm going on another tear. If you're a software engineer, learn how to think mechanistically about why you might be seeing these error messages, why you might be seeing these compiler messages or build problems, why you might be seeing these corrupted data in the database. Develop hypotheses, work to check the hypotheses, and you'll be able to perform at a much higher level than folks who are doomed to sort of just flail against it, just describe what's going on, but don't really have a good understanding about why we see these things. Malcolm.
Yeah, just maybe a bit more on the rant side, like that's an identified issue that you kind of brought up and stuff, but what are some good behaviors for those of us that, like, how does one develop that understanding? What are the best, like, how can one pop the hood on some of these things? What kind of behaviors would you recommend to pursue?
Great question. So one thing I will say is that there are some very good resources on in the software area, in the area of software development, on things like hypothesis-driven debugging and tools for systematically pursuing problems based on reasoning about the properties of the system, tracking down problems. And some of those are very thoughtful, and they can be used with tools. There are tools designed to help foster that sort of approach. Now, in the broader sphere of working with large data sets in whatever domain, maybe it's bioinformatics, maybe it's, in the sphere of plant sciences, maybe it's in computer systems and performance. In my view, it's about being able to articulate at a qualitative or quantitative level something about the structure of the system that is giving rise to the data. Now, there are times where we can articulate that in a quantitative way, sufficiently quantitative we can simulate it, okay? And that's really a lot of the focus of this course. But, in biology, for example, in systems biology, and with causal loop diagrams, applied more generally in system dynamics, et cetera, we have ways of articulating relationships between things that are about structure of the system. And one thing I've tried to convey to you in this course is that structure drives behavior. There's understandably, when you bring up models to people, they who've never seen a stock flow model before, never seen an Asian-based model before, a discrete event model. A lot of people just think, oh, it's just a bunch of data. To put it politely, that's nonsense. It's not merely reduced to a bunch of numbers. It is the structure of it that is at the heart of its behavior, at the heart of what's possible with it, at the heart of its dynamics and long-term evolution. The particular values of parameters do matter, but they matter within the sphere of tipping the behavior dictated by that structure. And I think one discovery in biology that in bioinformatics that was pretty big is the growing use of tools to systematically draw biological hypotheses and so on. And where these tools are not, where these diagrams are not arbitrary, they're not fully quantifiable in the sense you can simulate them, but they are specific in the sense of types of processes. Maybe it's methylation or phosphorylation that occur at certain processes, or transcription, or histone related dynamics for, as might be seen in epigenetics or what have you. And those processes, by illustrating the that in a visual way, we can reason about it. I know I met a person who had done a postdoc at MIT in biology, and he commented that one of the most powerful things that occurred to him during that postdoc was he saw how people in the lab at MIT were articulating hypotheses, trying to express them with models, as imperfect as they are, and using those to explain the data, advance different explanations for the data, realize that a certain explanation was not enough to explain patterns in the data, and to then using it to refine their thinking. Models are tools to refine thinking. I spoke with you about that from the very first day, right? They're thinking tools. They're prostheses for our thinking. We should not be slaves to them, but rather they should equip us to more quickly root out problems in our thinking. I articulated from this floor that it's not that models capture the truth. It's not that the model is the embodiment of the truth, or that it's a perfect approximation. No, but it may be good enough to help us spot cases where our understanding is off base, where it just doesn't hold water, it doesn't add up to explain processes in the world. And that's really valuable. It helps advance. It's not that models are the truth, they help speed us towards the truth by rooting out cherished, misconceptions about the situation. By helping us recognize, again, where our thinking doesn't add up, where it just doesn't come together. We're terrible about reasoning about that in our heads. But with a model, we can do so more systematically. And there indeed are books that have been written quite articulate about shaping this thinking. Sometimes it's called systems thinking. It's related to mechanistic thinking. But learning to reason in this way to explain observations from the world. And there are times, and don't get me wrong, I speak as a data scientist as well. There are times where our theory isn't there yet, where we just do not have good theory, and we don't have good hypotheses. And models, it's sometimes, many a time have I been with stakeholders, and they say, well, we don't have enough data to build a model. Then, as now, I have to restrain my language. That's one of the times, if you don't have data, if you're short of data, maybe you're not allowed to collect it because of political reasons, maybe, or ethical reasons. Maybe there's limitations because of cost. Maybe it's too expensive. Maybe it would take, we don't have the luxury of waiting for a randomized controlled trial that will require 20 years or what have you. But we don't have the data. That's when sometimes you can most valuably use models. But it's models used for a different purpose. It's models used to stir up theory, build theory, rather than to explicate theory, to sort of play out the logical consequences of that theory. A lot of our models, where we do have some recourse to data, play out the logical consequences of our theory and test the degree to which it's consistent. It's conciliant with that data. On the other hand, if you're short of data, often what you're doing is formulating models that help you think through what might be going on in the system in the absence of data. So what little data you have, you might still be able to reason where it came from, or it might motivate you to put down resources to collect certain types of data. So data is not a prerequisite for building models. It's a prerequisite for building models with certain goals in mind, certain purposes, but it calls us to build models for a different purpose, for building up our theory. So the enterprise of systems data science is not a widespread one. The community for data science is very large. The community for machine learning and AI is very, very large. I contributed some to that community. And similarly, the community for systems science and simulation modeling, dynamic modeling is reasonably large. Not quite as large, but reasonably large. But unfortunately, they too often are separated from each other. And in my view, the prospect of system science is much brighter yet if we can leverage many of the tools and insights that accompany data and use them to critically evaluate our models and to refine our models. And there's a whole set of methods which I teach that are not widely taught for this purpose. On the flip side, for AI machine learning, there's a set of methods from system science that can help you use your machine learning to much greater effect, to really speed deeper learning, et cetera. And the methods are not still to be discovered. They're right in front of us. And I have taught courses at this institution several times, in fact, which systematically tore through these types of needs and introduce students to some of these tools. There are tools that will take data and suggest structure of your model, or help you try to, arrive at some understanding of what the equations might be that govern a stock flow model, or that might hint you as to how complex that model has to be to explain the data. There's others that detect causality. If A is influencing B, if B is influencing A, if A is influencing B, and B is influencing A, or some other variable C is influencing both of them, but A and B are not influencing each other. These are really important things for teasing out causal connections. There's other methods that keep our models humble and correct them by observations from the world and keep them always with an ability to interpret the current situation and look forward. There's a wealth of techniques here, if you're savvy enough to want to combine those two worlds, which are oft pursued in isolation to their detriment. End rant 2. Okay. So thank you for the question, Malcolm.